In this video, I want to show you how the governing equations for turbulent analyses are developed. And in particular, I'm going to show you about equations that are based on the Reynolds average Navier Stokes approach. And you can see what's going to happen, I think, with this Reynolds average Navier Stokes equations in this illustration, where the left column shows the velocity structure in some experiments where there's a jet of fluid injected from the left to the right, and it's depicted in these next two columns here with two different types of simulations. And LES is showing a structure, a velocity structure that resembles the experiments. This is called the large eddy simulation. But this RANS, Reynolds average Navier Stokes, it shows that these velocity plumes are similar in shape, and the colors, the intensity of the velocity magnitudes are similar. But what we can see is that with the Reynolds average Navier-Stokes, the RANS, these small scale turbulent eddies that are in the data and that are in the large eddy simulation are absent here. They've been smoothed out, they've been averaged out, and indeed that averaging is at the heart of this approach. Okay, so with that in mind, what we're going to do is go through the Navier-Stokes equations and derive them in such a way that we've included these fluctuations in the flow caused by these vortices or these turbulent eddies. And we're going to start with the regular Navier-Stokes equations, where we've got conservation of mass and conservation of momentum. And this is a summary of some work that we've done earlier, where we have just the basic conservation equations. And we go through the development and we end up with conservation of mass right here. And similarly, we start with conservation equations for momentum, and we get the basic conservation of momentum equation here. And so that's the starting point. And what we'll do is look at how those equations are modified in the case of turbulence. And the thing that we'll do, the modification that we're going to make to account for turbulence, is that the variables, the velocity, the pressure, and the density, are going to be, we're going to think of these things as the sum of an average velocity or an average term and a fluctuating term. Okay, so if the velocity looks like this, and we saw that in fact this is what it looks like when a flow meter is put down into a river, then what we have is that there's a mean velocity that would be v bar, and then these fluctuations about the mean would be v prime. And the pressure is going to do something similar, and so is the density. Okay, so that's really at that's really the main conceptual model that we're starting with. Now, if we do that, and then we say that, we just basically make the substitution into the governing equations, then the momentum equation looks like this, where we started with something that looked like this, and the divergence of that, the density times the velocity plus the change in the rate of change of storage. And what we've done then is just substitute in. So m is the average plus the perturbation or the fluctuation, and then the density is the same, and the velocity is the same, like that. And So those just are expanded. And then we've got a term here where these also are okay. That's expanding them out. And then we take the average, where we recognize that when we're doing this numerical analysis, we're going to have an element, and we're going to assume that at some scale we're going to be averaging, taking an average parameter, and so we're going to put this bar over top of these variables to indicate the averaging, and that's what I've got written out here in the text. Okay, and so now there's a kind of a key concept which I call averaging rules here, and so we're gonna let's try taking a look at this. So if we actually let's go back up here to velocity, because we plotted that already, and we've seen some data in one of the earlier videos on this. So let's just take a look. I'm going to replot the velocity as something that fluctuates. There's the mean, and that's the fluctuation. So if I were to subtract off the mean, then I would have something like this. There's V bar, and then V fluctuation would be like this, where this is 0. Okay, and then I could add these two together and get that. All right. Well, now if I take the average of this fluctuation, then by definition, actually, this fluctuation has a mean of 0. Okay, because that's how I've defined it. I'm having just as much of the fluctuation below as above the average velocity. So the mean of the fluctuation is 0. And then at the same time, if I were to, I guess it follows directly that if I take the average or the time derivative of that, that also equals 0. And if I take the total velocity, where I take the average plus the fluctuation, and I take the average of that, then that's just going to equal the average. Okay, so if I take the average of this fluctuation, then if I take the average of the actual velocity, then I'm just going to end up with that average there. Okay, and so that's what I'm showing here in written out here in text. So there's the but this is applied to the density. There's the average of the fluctuating density. There's the time rate of change of the average of the fluctuating density. That's equal to 0. And then this is the average of the sum of the fluctuations and the mean, and that just equals the mean. Okay, so given that, we can go back up here and see that, well, that's just going to equal the average, and this is just going to equal the average, and that's just going to equal the average, and this is going to just equal the average here as well. And so we're going to get out of this is that through this averaging process, we're going to get an equation that is pretty much the same equation that we started with. Actually, I'm sorry, there is no velocity in this one. That'll be coming next. So this is just the average of the time rate of change of the density. Okay, so this thing in the conservation of mass, we just have a form that's the same as what we started with, or this guy here, but now these are the averages. Okay, so introducing this concept for dealing with the fluctuating terms, the velocities and the pressures with turbulence, hasn't really changed the mass conservation. So that's good. That's going to make things a bit easier. Um, but now we're going to take a look at momentum. So the momentum equation, the conservation is this. And actually, what I'm going to do, these v's are vectors, but I'm going to just leave the vector sign off of them because we're gonna use bars and primes um, for the averages and the perturbations, the fluctuations. All right, so now we go and do the same thing that we did before, where we've got fluctuations and averages. So that the body force is going to be the average plus the fluctuation. And then we've got the divergence of the flux. And I'm going to write this out. I'm going to just assume that the density is constant. So I'm not going to have the density fluctuating here. And we could do that. We could include it, but it's just going to make things longer and it won't really change the result here. So okay. Well, actually, let me just refresh that. Because I'm keeping the density constant, I'm just going to I'll have the density, and that's actually going to come out, but we'll just have the V bar plus V prime here. Okay, so we go and then average over these guys and get that. And now what's going to happen is we apply the averaging rules, and using the same averaging rules that we saw last time, this is just going to give us the average body force. And this here is just going to give us the average stress. And this is just going to give us the average velocity. But here we're gonna get something a bit different because this is the product of these two terms. So we're gonna have to multiply this out. So there's the average of that times that. There's that stuff, okay? And we're gonna then apply averages to these. Okay, so now we apply the averaging rules, and in this case, we have a constant times a fluctuation, and if we take that average, this thing here is 0 when we average the fluctuation. So that's going to be 0, and it shows up right there, so that's going to be 0. So those are both 0. Now, when we take the average of these two averages, that's just going to be the average. So here's what we're going to get. So here's the average velocity times the average velocity, and that all is averaged. That ends up just giving us this. These two go, and now here's and this is really, I think, a key point. So here we have these two velocities. These are two fluctuating velocities, and we take the average. So if we just have the average of one fluctuating velocity, okay, then if we just have that, then when we take the average, we just get 0. But if it's the product, then where you might not get 0, because if we take these two velocities and multiply them together, then if they're fluctuating at random, the average of that isn't necessarily going to be 0. If these two velocities are not correlated, then there's no reason to believe that it really would be zero. And so this thing stays. This thing is not going to be zero. It's going to have to stay in the analysis. Okay, so that's going to be the key result here, because that is going to give us a new term. Okay, so there's what we have. If we look back up here, then we've got an average body force there. We've got an average convective acceleration term there. And we've got a divergence of, actually, so let's see, this should be like that, right? And then here's this divergence applied to the stresses, which is what we had. And then this term is that term. So the thing that's new is right here. So we have another term that goes right in there that comes from this fluctuating stress or fluctuating velocities. And remember, these are the fluctuations that come from the turbulent vortices. Okay, so that's going to be the difference. Now, what we can do is go through, and when we did this before, we said, okay, well, this is the stresses, and we can introduce then a stress law for a linear viscous fluid, a Newtonian fluid, and we said that it's the pressure, and we use this. We're mixing the format a little bit, but we had a stress law that looks like, well, this will get us to the kind of the form that COMSOL is using. So there's velocity, and there's the velocity of the transpose. Okay, so this was the stress law. Here's the pressure, and here are this is the strain rates, and there's the viscosity. Okay, so that got substituted in there, and then we went through and did the analysis, and we substituted in there. We took the divergence, and we end up with so that's all well and good. This is what we had earlier, except this term here is new. Okay, so what I'm going to do now is rearrange this in a form that is, well, we're going to take this stuff over on the left side, and, well, we're going to take that and that and that over on the left side, and this stuff is going to stay over on the right side. Okay, so just rearranging things a bit. There's the pressure gradient term, and then the divergence applied to this stuff here. That's going to be, there's the viscosity, and strain rate transpose, or all of this together is the strain rate tensor. And then here's the key thing, that term right there, see how we've got del dot rho VV? So here's del dot this stuff, and we're going to add to it, right? It's going to come over here, so it's a negative sign, and it's going to be rho V prime bars, and then we close it. Okay, so there's del dot this stuff right there, and del dot that stuff. Okay, so that's expressed right here. And then we've got the right-hand side, which is this one and this stuff right here, okay? All right, so that's what we get just rearranging. And I have it written out here in text, so maybe it's a little bit easier to read. There's the body force, the pressure gradient, and this is the shear stresses, and there's the viscosity, and then here's the term that has these velocity fluctuations from turbulence in it. This is convective, and these are the two acceleration terms, the convection and the transient accelerations. Okay? All right, so what we've got with all of this is that is now new. Okay, so here, I just rewrote that stuff. And here it is written out in Einstein notation, where each one of these terms just now has a different notation. And this term right there is there. And I did this because what we can see then is if you write out these velocities like that, then these velocities are this. And what this means is that you have these are each. This is a 3D component, right? So it's a three-dimensional vector, and when I multiply it together, then I get these different terms. So this is the velocity, the fluctuating velocity in the x1 direction, and it's the product of those two. And here it's in x1 and x2, product of that, and x1 and x3. Okay, so here's why we can see that this is not zero, because if this velocity is, if it's just fluctuating randomly, then there's no reason why this would be correlated to that. So there's no reason why the velocity would end up averaging out to be zero. So what we end up with then is this thing here, which write it out like that, and it's this 3 by 3 matrix. It's a tensor quantity, and it's a symmetric tensor, so these are the same. These are equal to each other. And so what that means, though, is that we've got 6 new terms. That these are new terms that we don't know. So these are 6 new unknowns. Okay, so that's that's a problem, because we have got the same governing equations that we used to have, conservation of mass and conservation of momentum, but we've got these new unknowns. So we now have more unknowns than we have equations, and we don't really have a way to solve that. So that's what's called the closure problem. We've introduced more unknowns, but we haven't introduced more equations. So we can't close the problem. We can't solve it. Okay, so that's a problem, and what we're going to do is introduce an approach that has been known for a long time. This is well, let me show you how it works. All right, so this is what we've got. This is the momentum conservation, and here is the term that has these new unknowns in it. So what we're going to, well, first of all, what we're going to recognize is that the way that I've kind of written this intentionally like this, where it's this and this are together in these parentheses. So this is these are the viscous stresses, the viscous dissipation formed by these shear stresses. And what we're going to say is that this term here, which is the velocity fluctuations, it is also going to contribute to the flow as viscous in a way that's similar to viscous dissipation. Okay, these turbulent eddies are going to be using up energy just like viscous dissipation does. And in fact, what we saw in the talk last time was that we've got these vortices that we've got big ones and they break up into smaller ones and they break up into smaller ones. And we've got this whole cascading size of from large to small of these eddies, and then at the very smallest scale, the turbulent eddies dissipate energy in as viscous losses. And so I think conceptually it seems reasonable to treat this as if it's also or analogous to viscous dissipation. So we're going to take this term and actually this is going to be most analogous. So we're going to take this term, which I just lifted from there, and we're going to say that it equals, we can represent that this way, with an effective viscosity times the strain rates. So this term here, it's the same expression that we have there for the shear stresses, but we're going to have now a new term for this, we're going to have a new viscosity here. This is the eddy viscosity, and it's a viscosity that is it's a term that behaves like viscosity in the way that it dissipates energy, but it's a result of these turbulent eddies. Okay, so this is really a key concept for how we're going to analyze turbulence. This was recognized, these stresses, this approach was recognized a long time ago by Reynolds, Osborne Reynolds. He's a famous person working in fluid mechanics. And then this approach is credited to Bozanesque, also quite a while ago. Now, in general, in turbulent flow, this effective viscosity, the turbulent viscosity or an eddy viscosity, is much, much greater than the actual viscosity of the fluid. So the energy that gets dissipated in these turbulent eddies is much greater than the energy that's dissipated just by shear in the fluid itself. So it ends up being quite important. Okay, so the way that that's going to work then is we're going to take the momentum conservation and we're going to replace this with that. And that's going to allow us to have two terms that are multiplied by this. Basically, it gives us this. So this is reduced or is transformed into that, where we now have, so it's kind of a good news and bad news. The good news is we got rid of these fluctuating velocities. The bad news is we now have that thing, that turbulent viscosity that we have to deal with. And I guess when I look at this, I see that we've got U's and V's, that this is just the kind of a mixing of formatting. These are the same. These are both velocities. Okay, so now we've got eddy viscosity that we're going to have to work on. So these are the Reynolds stresses, and this approach then is essentially now giving us this form for the Navier Stokes, and this is the same form that we had. Remember when we did the mass balance, we got the same form, except everything was averaged. Now we've got the same form, except we've got this term here. The viscosity is now the sum of the actual viscosity and this turbulent viscosity. Okay, so this is now the Reynolds average Navier Stokes, or RANS. Okay, so now we need to come up with a solution for this, and there are a bunch of different ones. Here are a listing of some of them. They have got different numbers of equations. Zero equation that includes a mixing length. One equation by these guys, Spallard and Almaraz. Two equation models that are these are probably the most common ones, K-epsilon and K-omega. And then there's a 7 equation model that's also available. Within each one of these, there are several different versions of these. So there are a variety of ways of solving this Reynolds average Navier Stokes. What I want to do is take a look at one of these, the K-epsilon model. Okay, so K-epsilon, and what we have to do, remember what we did here was to introduce this new viscosity. And so we have to have a way of coming up with what this viscosity is. It's a term, it behaves like viscosity, but it's a result of the turbulence. Okay, so we have to have a way to calculate that. And in K-epsilon, the way that this is done is to introduce two new terms, and not too surprisingly, it's K and epsilon. So K is the turbulent kinetic energy. So it's the kinetic energy in these vortices, and epsilon is the rate at which energy is dissipated by these turbulent eddies. Okay, so in the K-epsilon method, this viscosity term is equal to this. So that's a constant, that's the fluid density, and there's K and epsilon. Okay, so if we can calculate K and epsilon, we can come up with the viscosity, and then we can deal with the momentum. Okay, well, that's getting us started. What we've got to do now is come up with ways to deal with these two. So, on one hand, it seems like we get a way to solve for the turbulent or the viscosity, the eddy viscosity. But on the other hand, maybe it's a step back because now we've got two unknowns. We solved for this, but now we've got two more things that are unknown. Okay, but we've got a way of dealing with these because the turbulent kinetic energy and the turbulent dissipation rate, we're going to say are conserved within the flow, and so we can apply our regular conservation approach and come up with governing equations for those terms. And so here's how we're going to do it. This is our standard conservation equation, and for the turbulent kinetic energy, the C term, the turbulent kinetic energy per unit volume of the control volume, ends up being K times the density of the fluid. So C is equal to that when we're doing conservation of the turbulent kinetic energy. The diffusion term is the gradient of K times the kinematic viscosity. The advection of turbulent kinetic energy is the velocity times C, right? That was just our standard approach for advection. It's just the velocity times our dependent variable there. We substitute in and we get velocity times K times rho. And then, as it turns out, there's a source term for turbulent kinetic energy that has that form. Okay, and there's that'll be another term, and that'll be that's the epsilon. Okay, so we substitute all this stuff in, and here's the governing equation for turbulent kinetic energy. Okay, and now, this, if you look at it at first blush, it might be a little bit confusing, but it's really just this thing applied out where the fluxes are, we've got a diffusive flux, or we've got a advective flux and a diffusive flux of the kinetic energy. There's the change in storage, and there's the source. Okay, so we see how to develop the governing equation for K. We do the same thing for epsilon, work through it, and we get another governing equation like this one for epsilon. Okay, so now we've got additional governing equations. So remember, the closure problem was we had more unknowns than equations, and we couldn't close it, we couldn't solve it. But now, through this approach, by setting up this viscosity term and then coming up with a way to relate that to these two additional terms, we've got additional equations that we can solve. Okay, so that is then giving us this path forward, and that in a nutshell is what's happening with K epsilon. This is probably the most common method for analyzing turbulent flows. It's relatively simple to implement, and the operational word here is relatively because it's simpler than the other methods, but it's still, we'll see. I'll show you the equations. It ends up being 4 governing equations, but it's simpler than some of the other approaches, and it works pretty well. It leads to stable calculations and converges relatively easily. Again, relative is the operational word here, and it gives decent results for many flows. The downside is that it doesn't work too well for a variety of different types of flows that you might be interested in, swirling flows and jets and various other things. So there are some things that it doesn't really work so well on. It's only valid for turbulent flows. So for lower flows, in maybe the transition zone, it's not going to work too well for. And so this leaves the door open for other methods, and there, as we saw, a variety of other possible ways of doing it. Okay, but this is a pretty important one. So if you implement this in COMSOL, you'll see that it's got a turbulent node or a physics node there with the K epsilon turbulence, and then if you look at the equations, you'll get something that looks like this. And so I think we can kind of parse this out and see what's going on here. So that's the momentum conservation. This is there's the convective acceleration and the transient acceleration, and then on this side there's the body force, and this is there's the pressure term, and then that ends up being the shear stresses. And let's see, so K, it's just kind of lumped together. There it is. So there are the strain rate terms, and then there are the two viscosities, the actual viscosity and the turbulent viscosity. Okay, so that I think we recognize. Here, this is the divergence of the flux is equal to 0, so that's mass conservation. So I think we can check off those. Now here, that thing, well, look, that's going to be this change of storage of K. This is a convection of K, and this is a source term for K, and then this is this diffusion of K. Okay, so this is the governing equation, basically conservation of turbulent kinetic energy, and then here's the term for epsilon. So we've got similar things for epsilon. That's a source, diffusion, advection, and change in storage. Okay, so that's what's going on there. And then another governing equation is this thing here, which is the expression for the turbulent viscosity. Okay, so we're going to be calculating K and epsilon, and then they're going to go in there and be used to calculate that term, which is needed for there. And let's see, in the source term, we have that thing, pk, that ends up right there and right there. And so that's defined right there. Okay, so those are the governing equations. What we see is we've got these additional equations that account for the additional things that we need to solve for. I guess also if you take a look down here, this is here you can select the Reynolds average, Navier Stokes. There are in some cases you can also use the large eddy simulation within the RANS. There are several different models. Here's K epsilon, and then there are others, K omega. We saw that one, the Spalard anomalous. And a variety of others. And I think actually if you scroll down, there are even more than these 5. Okay, so there are a variety of options to pick from. And this is just an introduction into this one method here. Okay, so the overview is that when we do this analysis of turbulence, we've got these dependent variables. We've got 4 dependent variables, pressure and velocity. With laminar flow, that was it. We just had pressure and velocity as the dependent variables. Now we've also got the kinetic energy and the dissipation. The properties that we need to solve for, density and viscosity, or the properties that we need to give we need to provide, the density of the fluid and the viscosity of the fluid. We have now 4 governing equations, mass and momentum, and then we saw these 2 governing equations. Also, they're conservation equations. And we need now boundary conditions for pressure, velocity, K, and epsilon. Okay, so the boundary conditions end up being a little more complicated than what we've seen for laminar flow, but we have two basic types where we can specify the pressure or specify the velocity. For the specified pressure, if P1 is the pressure we specify, what we saw last time was we could just say that the pressure at the boundary is equal to some specified pressure. But now we've got it's a little more complicated, where we say that the pressure is equal to this term, and here's I'm using the same format that comsol uses, where this K is this term from the viscous stresses, and now with the turbulent viscosity. And then we have additional terms for just when we specify the pressure. We also are specifying that that's the tangential vector, so the tangential velocity is 0. And we've got expressions for K and epsilon, and these are going to be functions of the velocity and this K. Often these K's and epsilons have terms in them where they're linked. These expressions have the turbulence intensity and the turbulence length scale. These things that are that need to be specified in some way. COMSOL has ways of estimating some of these terms, so it's doing some of this. It's simplifying this in some ways. But if you look at the boundary conditions, when you specify the pressure, you'll see these different expressions, and you'll see how they're being calculated. When you specify the velocity, again, we can specify the velocity normal to the boundary, and we've got to then specify, when you do that, you would specify that the velocity normal to the boundary is equal to some term that you give it. Then you have equations for K and epsilon as well, and these are some functions that have a variety of terms in them, including the turbulent intensity and turbulence length scale. If it's a no slip boundary, this is what we use for laminar flow, and we're gonna specify that we're gonna have a specification for the velocity, but then we also have to specify, in this case, the gradient of k normal to the boundary, and we have another term for epsilon. And if we have slip at the boundary, this will be a possible condition. Will require that the flow normal to the boundary is 0, but it's possible for there to be slip, and we have some conditions for that. Okay, so the velocities at the boundary are a bit more complicated. There's some other aspects related to the boundary conditions under turbulence that are also need to be considered with just what the structure of the boundary layer is going to be like, and that'll be something that we can take up later. Okay, so that's just going to be an introduction into this Reynolds average Navier Stokes, and in particular the K-epsilon approach, and how it's included in COMSOL.